Bob picks a real number between 0 and 1, while Billy picks a real number between 1 and 2. What's the probability that Billy's number is at least twice as big as Bob's number? With a probability question like this, it seems fitting to break it up into some cases. However, notice that Bob and Billy can pick any single real number between certain intervals, in this case 0, 1, and 1 and 2. That means there are going to be an infinite number of cases here. Bob could pick 0.1735, Billy could pick 1.1792. As you can see, like there's no finite amount of cases between two certain picks between these two people. So when you have a probability question like this where there are an infinite number of cases, one thing you can do is use geometric probability. Before we get into that though, it's important to realize that if Bob picks a number between 0 and 0.5, so for instance, if his number was, I don't know, 0.3, Billy will always have a number that's at least twice as big. The chance of Bob picking a number between 0 and 0.5 is 1/2 because the full interval is just 1. So we can write down 1/2 is the chance that Bob picks a number between 0 and 0.5, and in that probability, the chance of Billy having a number that's at least twice as big as Bob's number is 1. So that's our first case, technically, in that if Bob picks a number between 0 and 0.5, Billy always has a number that's at least twice as big. But the other case is, and there's a 1/2 chance probability for that too, if Bob has a number between 0.5 and 1. In that case, it gets a little bit more complicated. This is where we're going to use geometric probability. So let's make this graph right here with the y-axis and an x-axis. Let's say that Bob's guess rather, is on the x-axis and Billy is on the y-axis. And in this case, remember, we're saying that Bob picks a number between 0.5 and 1. So let's say at the origin here, the x value is 0.5, and at the very end over here, say, it's 1. And for Billy, he can pick any number between 1 and 2. So at the origin, it's 1, and let's say over here, that's 2. That's the largest number he can get. Let's look at the endpoints for Bob's guess. Let's say Bob chooses 1. In that case, the only number from Billy that will be at least twice as big is 2. So 1, 2 is the only possible option for this condition to be true, Billy's number to be at least twice as big as Bob. But what about 0.5? If Bob chooses 0.5, however, all the real numbers rather, from 1 to 2 will work. So there's a whole line here. Let's look at a number in the middle. What if Bob chooses 0.75? What numbers work in that case? Well, the number that's twice as big as 0.75 is 1.5. Let's just put it over here, 1.5. But then any number between 1.5 and 2 would work. So kind of this line of values would work to satisfy this condition. What about, let's say, 0.9? Why not? 0.9. Well, in that case, all numbers 1.8 and up would work. 1.8 to 2. Those numbers would work. And as we choose more and more values, we'll see that there's kind of a line that's getting made here. As you can see, dots going down like this. Starting from 0.5, you can't really see the dot here, but it's starting from 0.5 and going all the way to 1. And as the numbers go up, the line goes up to 2. Let's connect all these lines together. Not the prettiest connection, but basically the point that's trying to be made here is that what does this look like now? If we put a cap here, this looks like a triangle. Pretty much all of these values in here satisfy the condition. And because of that, we can see that from a geometric perspective, in a rectangle of options in which the x value can go from 0.5 to 1 and the y value can go from 1 to 2, the only values that work is this triangle right here. But what's the value of this triangle? What's the area of this triangle divided by the set of all possible values? Well, what's the area of this entire rectangle? This rectangle, not very pretty, but this rectangle that goes from 0.5 to 1 and then 1 to 2. Well, the area of a rectangle is just base times height. The base in this case is 0.5 to 1 or 0.5, and the height is 1 to 2 or 1, a length of 1. So the full area is 0.5. But we want half of that area because it's this triangle right here. And what's the area of this triangle? Well, 1/2 times base times height. We said that the base times height was 0.5, and 1/2 that, because the area of a triangle is just 1/2 times base times height, is 0.25. So therefore, of all these cases, the ratio of cases in which the condition is met versus cases in which the condition is not met is 0.25 divided by 0.5, which is 0.5. And what does this number mean? Well, this number isn't the answer, by the way, not the answer at all. In fact, this number gets plugged into here, 0.5. And the reason for that is because, remember, we split this problem up into two cases. The first case is when Bob's number was between 0 and 0.5, and the second case was when Bob's number was between 0.5 and 1. For the case in which Bob's number was between 0 and 0.5, we will always satisfy this condition. But for the case in which Bob's number is between 0.5 and 1, we'll satisfy that condition 1/2 of the time. So we get 1/2 times 1 plus 1/2 times 1/2, or 1/4. 1/2 plus 1/4 is 3/4, or 0.75, or 75% of the time. 75% of the time, Billy's number is at least twice as big as Bob's number. And we are done.